So this is the third lecture about eigenvalues and eigenvectors. And in fact, I'm actually don't go that much into depth about sort of the modern algorithms for how to compute eigenvectors and eigenvalues. So these can be pretty sophisticated. But what I want to do is start to outline some of the key concepts that are required and how sort of in some sense these generic algorithms are structured to compute these important quantities that we use over and over and over again. The other thing that's kind of I'd like to just point out is software packages like Python and Matlab. One of the really compelling parts about having software like this is that people wrote really great code and you have access to it super easily. So like in Matlab, you can say eigs and then put a matrix in there, and fairly sophisticated things are going on in the background there to find you all your eigenvalues and eigenvectors, so you don't have to lift a finger, right? And then you can go solve your science problems with that. And so, and even today, I'll highlight some of this. Even Trefethen really kicks down the road some of the more state-of-the-art methods, but more focuses on sort of classical methods and how would you go about doing these things. And last time we talked about Rayleigh quotients, and we talked about not only that, but some Rayleigh quotient iteration, which is you can look for different eigenvalues by putting an artificial parameter mu in there. And so we're going to continue on this theme about how do you start setting up generic architectures to look for eigenvalues and eigenfunctions. Okay, or eigenvalues and eigenvectors. So computing eigendecompositions. All right, so that's what we're interested in, is what are the algorithms we want to go after here that will get us towards understanding these concepts. So let's talk about what generally goes on in these algorithms. And in fact, I didn't specify much because we were doing sort of, in some sense, these Rayleigh quotient type calculations, which were just iterative procedures where you form this quotient, which basically created a quadratic functional, which allowed you to create a convex landscape in which when you started to iterate, the solution converges to the minimum, and that minimum is exactly where your eigenvalue sits and your eigenvectors accordingly, okay? But really what we want to do is start thinking about generic matrices and also how do we want to start framing this problem and speeding the problem up. And it turns out when you start to go around and do computing algorithms, for the most part, what happens is there's two steps that occur for computing the eigenvalues and eigenvectors of a matrix. So normally, the first step of any of these algorithms is first to do some kind of factorization. And in particular, what's typically done is what's called a sure factorization. We'll talk about that what is in a minute. But basically what this is allowing you to do is take the matrix that you're given, find a better way to represent it. In fact, part of what we're going to do here is basically produce here a self-similarity transformation to a matrix which is easier to compute the eigenvalues on. Okay? Now remember, a self-similarity transformation is if I move from one if two matrices are self-similar, they share the same eigenvalues and eigenvectors. So what I want to do is try to figure out, is there a constructive algorithm that moves me towards a better framework or self-similar framework to do this last manipulation I need, which is to find the eigenvalues and eigenvectors. Step two is after you've done this factorization, and a lot of these factorization, what we've been learning out about the whole time here is things like QR factorization, LU factorization, QR factorization. all these are sort of these principal methods where you can apply recursively a set of matrices to just in some, I wouldn't say straightforward manner, but in a progressive manner, find and construct a solution or a decomposition. Here, what we do is that as the first step, but in the second step, what we do is we iterate then to find the eigenvalues. And iteration is a very different thing than we've been doing so far. In fact, we're going to turn our focus to iteration, solving AX equal to B through iteration in the next set of lectures. But right now, we're going to use the same concept here. So in other words, this here is sort of, in some sense, perfectly prescribed. I give you an algorithm, it just goes and it does it, and it finishes this in a finite amount of time. Iteration is a process where I just sit in my loop, and I'm looking for this thing to converge to some values. Technically speaking, you'd be in this loop forever. But of course, we never are in here forever. We do it for a finite amount of time, and then we truncate this iteration procedure at some point. So this is the basic structure of all modern day eigenvalue and eigenvector algorithms. What you're doing is first do a self-similarity transformation to a simpler matrix. And from that simpler matrix, iterate to the conclusion, which is iterate this thing to find the eigenvalues and eigenvectors. And then since you have the similarity transform, you get the eigenvalues and you come back and compute your eigenvectors. Okay? So let's talk about this step one. Step one is the Shor factorization. And the Shor factorization is just a self-similar transformation that takes the following form, where Q is exactly what you might expect. Q is some unitary transformation. Remember the Q, we used this before when we did QR decomposition. In fact, there are some ways to compute eigenvalues where you, in fact, for a long time, we used the QR algorithm as a way to do this decomposition. So the QR algorithm was, in fact, at the very underpinnings of how to compute eigenvalues and eigenvectors. And this Q represents a unitary transformation, okay? So Q is unitary, and T is going to be upper triangular. So this is our goal, is find a way to decompose A into the Shor decomposition. And once I have it in this form, what I'm going to go do then is take that T matrix, and in that T matrix, I'm going to find an iterative procedure to go find the eigenvalues and eigenvectors. So what I'd like to do is set up a T that's advantageous for me. Here it's an upper triangular form. And once I've done that, now I could just iterate to get the eigenvalues. And then if I want to get the eigenvectors back, I can easily do that because now I have the eigenvalues, eigenvector pairings in the self-similar form. So how do we accomplish this Q and this Q transpose here, this unitary matrix, right? Q, Q star, right? So these are, the nice thing is this is the inverse. And by the way, notice how much like an eigenvalue decomposition it looks like, right? Remember an eigenvalue decomposition looks something like this, right? Eigenvectors, the inverse of the eigenvectors plus some diagonal matrix. Notice that I have not constrained this to be diagonal, right? If I constrain this to be diagonal, I have exactly an eigendecomposition. I've constrained this to be upper triangular, which is not as harsh of a constraint. It's a little bit easier constraint to satisfy. And I've also done it in such a way that make this upper triangular and allow this to be unitary so that the inverse, I don't have to compute inverses, okay? So how can this be done? Well, how did we learn how to do these decompositions? What we learned to do decompositions is find matrices to multiply this by, to basically, when you want to make this upper triangular, you have to start zeroing out below the diagonals to make that happen. This is exactly what we did in LU decomposition, right? We found these matrices L of K, which would zero out everything below a given diagonal as we went down this thing and put it in upper triangular form. So something similar is going to happen here. So what we want to do is think about representing Q and Q star actually as something like this. A series of QJs times A So we want to think about how to multiply on the left and the right of A. And so notice what this is, right? So this is going to be some matrix Q star, which when I multiply Q on the right, I'm going to get to here. And so we want all this to be basically put me into upper triangular form. So what are the matrices that I construct that I multiply on both sides to zero things out correctly so I get this in the upper triangular form? So notice how much like a LU decomposition it looks like, right? Remember that in the LU decomposition, all we were trying to do is make an upper and lower triangular form by repeated multiplication by some matrix L of K, L1, L2, L3, where each one of them started setting zeros below the diagonal. Similar structure, except now I'm using unitary matrices. In the LU decomposition, there was no unitary matrix there. Right? It was just find me two matrices, L and U, which were a combination of submatrices. By the way, let's talk about something important. What if A is Hermitian? That means it's symmetric, right? So if A is equal to A star, it means it's Hermitian, which means it's symmetric. It means if I take the transpose, it looks, the complex conjugate transpose, it looks the same. In fact, let's assume it's real. So really all this does is it transposes the matrix. So it means you're symmetric about the diagonal. But because this is a self-similar transformation, T also has to be Hermitian. Now there's huge consequences for that. If T is Hermitian, remember all I was trying to do was make T upper triangular. So all the zeros, so think about what this matrix looks like. But if this is Hermitian, if T is Hermitian, then in fact, T has to be diagonal, right? Because it has to be symmetric. And if it's upper triangular form like this, it won't be symmetric. The only way it can be symmetric is if in fact that's diagonal. So at least for the case in which we have Hermitian matrices, this process of factorization, the Shor factorization, is going to give me something that's actually going to give me something towards a diagonal. Okay, and that's just a product of a consequence of the fact that a Hermitian matrix under self-similarity transformation is another Hermitian matrix, which is upper triangular has to be diagonal. Okay, so let's talk about the procedure of how we want to actually do this kind of operations. So I want to draw it graphically. And of course, we've spent some time, like with LU and others, to know that, oh, there's a formal procedure for computing, how to do these things, right? How to construct these matrices to do this. We spent a lot of time talking about projectors and LU factorization. So hopefully all of this will seem familiar. And so I'm going to give you the highlights of this. And where we're going to end today is how do you compute the SVD? Because we actually never talked about how we computed it. We've used it, but we've never talked about like, well, actually, what is the algorithm for computing the SVD? Okay. So let's take some matrix. Here it is, some 5 by 5, something like this. This is A. So the goal, step one, and let's assume for a moment that in fact, it's not Hermitian. So this is just some generic matrix A, no special properties. So step one of this procedure is going to be to do a decomposition into what's called Hessenberg form. In Hessenberg form, has this very nice property. What you're trying to do is do this. Set everything below one subdiagonal to 0. So step 1 is 0 everything, not on the diagonal, but one below the diagonal. So this is upper Hessenberg form, okay? So it looks a lot like LU, right? Where it's like, how do I do this? How do I go about doing this? Remember in LU, you could zero out everything and make it upper triangular and then do back substitution. But here we're going to do it in Hessenberg form. And then in step 2, once it's in this form, you want to set up an iteration procedure that basically turns that into a diagonal. So here's the important things about what I'm drawing here. And this is what this graph represents, or this picture represents. The first step is constructive. In other words, I tell you a prescription, an algorithm, just go through this and produce that matrix. The second step is the iteration step, just like I drew before. So the first step is transform the matrix. The second step is then to say, from this matrix, set up an iterative procedure so that you iterate, just like we did in power iterations. Of course, we're not going to use power iterations, we're going to use fancier things than that, but iterate towards a diagonal matrix and then pull off your eigenvalues and eigenvectors. That's going to be the generic procedure. And this is this matrix T that you get out. And this is a matrix H. So what I'd like to point out is this is the generic architecture for all of these eigenvalue, eigenvector decomposition algorithms that are out there. Now, importantly, there are a lot of them. And there have been a lot of different ones that since the 1960s that have been around. And so I want to just highlight sort of the generic structure of all of them. And then the procedure for doing this here especially is quite a bit, has a lot of variability, okay? And so just want to throw that out there. So the state-of-the-art methods for doing this are kind of pretty fancy and pretty nice. By the way, let's redraw this figure, assuming that A is Hermitian. What happens if A is equal to A star? Well, we have the same starting matrix A. And then in step 1, if in fact it is Hermitian, you get something very nice to happen, which is in step 1, it's very easy to transform this into a tridiagonal matrix of this form. So three diagonals matter, the center diagonal plus the upper and lower diagonals off of the center diagonal, okay? So this is just a property because you have symmetry in the matrix A. And because of that symmetry, it allows you, instead of just removing all these zeros, you can remove all those zeros up there due to symmetry. So you get this form here. So it's kind of like this nice Hessenberg form where all you guys are zeroed out on top too. And finally, step 2. Use an iteration procedure to finish you off, to take you from this form here, iterate towards the solution there. Okay, so 2-step process, a reduction of form, second, iterate to conclusion. Okay, so that's the general process that's basically out in all of these eigenvalue solved problems. You don't just take the matrix A and go look for eigenvalues. You know, what I showed you with Rayleigh quotient and so forth, and some of that architecture I showed in the last lecture is not what people actually do in practice for computing these eigenvalues. It's an idea that's very old, pre-60s, right? If you're going to compute eigenvalues, largest eigenvalues, hams, you do power iterations. But you know, people don't really do power iterations for these eigenvalue solvers. And that's been since the 60s. People have done more sophisticated things. All right. So let's talk about how to actually produce this decomposition in practice. okay? So I'm going to start off, and I'm going to just keep drawing pictures today. Today is a day for drawing, okay? I want to draw some pictures, but hopefully you'll see the algorithms. And notice, we have in the past lectures looked at these pictures and shown how to produce these decompositions we want to do in a principled way. So I'm going to go ahead and talk about how do we do these actually here in principle, and what are the decompositions we need to carry them out. All right. So let's start off with the idea of how to do a reduction to either Hessenberg or triangular form. Okay. So I'm going to start off with a matrix A. Generic here. The first thing I want to do, and I've already shown you what happens if you do a bunch of these, but I'm going to show you sort of the process of that it's a recursive process towards systematically going through this and doing the reduction we need. So first of all, if I wanted to put in this upper Hessenberg form, I have to zero out all of this columns below, the one diagonal below. So I want to zero everything out here. So the objective then is to construct, it's going to be my matrix, I'm going to call it Q1 star. And what Q1 star is going to do, its entire focus is to remove this. Okay, so what it should produce for you is a new matrix that looks like this. All I've done is zeroed out all the elements below here. If you go back and look at your LU decomposition, we can easily construct these matrices, right? They're just saying, if I want to zero everything out below here, it looks a lot like that L of K that we built, okay? You can leave everything else alone, doesn't even matter. Like, you just want to zero this out. But now I want to do one other thing. Once you've done this, you now want to set yourself up to have another matrix here, Q1, in which you change all these values here so that this thing here is self-similar. So this here is Q1 star A. This one here, Q1 star A, Q1. So whatever this matrix Q1 star is that I found for here, I want to now post multiply on the right. Remember, this is going to be unitary. So by post multiplying on the right, this is now, so you still have these zeroed out here, but now all these values change in here, but in such a way that this is self-similar to what you started with. So that's the key. Remember, in LU, all we did is we did this and then remove the next and remove the next, remove the next. Here it says remove this, but then multiply, set it up and structure it in such a way that it's unitary, so that I'm going to multiply on the right by that, the inverse of that. In other words, if that's Q1 star, it's Q1, which I get a new matrix, but this matrix here is self-similar to what I started with. That's the key. I am building recursively a set of self-similar structures as I go through this algorithm. Step one, build me a self-similar matrix where it's zero behind here. Okay? Step two, now go to the next diagonal, make it all zeros. So now I'm going to do is find a new matrix. I'm going to continue right here. Hopefully this will work. Q2 star, where what I want to do is already have X and zeros. I want X and X and X and zeros below there. Take this out here. So this is Q1 star A. So now I'm going to find this Q2 star such that this is true. I just zeroed out everything below, one below the diagonal. Find that matrix Q2 star that does it. And once you've found this, you say, okay, good. So this now is, I hope this shows up on the screen there below. It's Q, can you guys see this? Well, Q2 star, Q1 star, A, Q1.
Yes.
Yeah.
Awesome, thank you. There we go, so I have that. And now what I want to do is take that same matrix, multiply, since it's unitary, multiply on the right by it, so that what I'm going to get out is something self-similar. So that's going to basically give me here Q2 where now all these blocks here got changed because of this Q2, but this here now is, in fact, a self-similar matrix, right? So this is really nice. Notice how this procedure is going for us. I'm finding a constructive way to keep putting together a series of self-similar transformations so that at the end of the day, what I've done is done this Shor decomposition. Okay? And notice the only difference between this and LU is that in LU, I never bother to do this. I just simply say, once at 0, move to the next row, keep setting everything below the diagonal 0. Here, I'm making this thing symmetric in some sense, Q1 star Q1, so that I preserve the self-similarity structure, because the only things we want right now are eigenvalues and eigenvectors.
I have a question.
Yes.
What metric of self-similarity are we using here? Are we using spatial distance, or I guess I've heard there are a number of different metrics of self-similarity.
Yeah, all we care about is the eigenvalues are the same.
Okay.
That's it. Okay, so what we're going for here is, one way to think about it is, when you take when you look at how to compute eigenvalues and eigenvectors, right, it's the determinant of A minus lambda I. And you want to look at that characteristic polynomial. And that gives you a polynomial equation for which you have to solve the roots for. What I want is to decompose this so that I get the same characteristic equation. That's it. And what I've got here is this procedure to do it. I'm just changing what we've done before to enforce this structure at each step. It's more work, because in LU, I just had to go through it from the left side and do L of K operations. Here I have to do 2 operations per side, but it buys me a self-similarity at the end. And that's exactly what I want to enforce for this thing. By the way, if this is Hermitian, here's what's kind of interesting. If this is Hermitian, when you start to do this, because of symmetry, when you take this and this, you start now to zero out columns here, so this thing ends up with a diagonal form. Okay? So that's and here we're just doing it very generically for any matrix A. But the nice thing, Hermitian is really nice because Hermitian has beautiful properties about symmetry here. And then when you do this decomposition, that symmetry all of a sudden starts making things disappear very nicely for you. Okay, so that's a generic procedure. And because I love these Hermitian matrices, if we could only work with Hermitian matrices, it'd be amazing, right? That's one of the things in life. It'd be nice because all of the eigenvalues would be real, and they'd be distinct. And so we'd have all these really nice properties. And in fact, the eigenvectors would be orthogonal to each other. So Hermitian matrices have these beautiful properties, right? And it almost seems too good to be true when you make a Hermitian matrix. So, and because generically you don't have a Hermitian matrix, you just have some matrix A. But this is the general procedure for doing this. And once I've done this decomposition, then I set it up to do iterations from there. And then iteration structures, we're going to talk about iteration in the next set of lectures. So I'm not going to talk too much about how to do this, but the idea here is you set up an iteration much like we did with the power iterations. And you just, once you've got it into this Schur and Hessenberg form, it allows you to then just simply iterate on this matrix you get out to find your eigenvalues and eigenvectors. But I want to turn my attention now to the most important of the eigenvalue decompositions that we want, which is related to computing the SVD. Notice that to this point, we really haven't talked about computing the SVD. All we've done is, you know, if you're in Matlab, you say, you could just do the SVD by saying SVDA. You're done, right? And the question is, what's actually under the hood of that computation to produce for you the U columns, the V columns, and that diagonal matrix C. Okay? So that's what we want to address next, because that's one of the very important applications of this kind of procedure. All right. Plus, I'm a huge fan of the SVD. I think that's your most important of the matrix decompositions that you have. And so understanding how the computation goes, and remember that the SVD always has a decomposition. So that's also special, right? That eigenvalue decompositions aren't guaranteed to hold, but SVD decompositions are absolutely guaranteed to hold for any matrix. So what's going on with the SVD? What's so special about it? How do we compute it in practice? The first thing I want to highlight to you goes back to the early lectures about the SVD, which is there's two properties I showed related to SVD, which is A star A times V is equal to VC, and A star U is equal to UC. But remember that A is equal to U to V star. You work in two bases, U and V, and this diagonal matrix C. So these are two unitary transformations. Unlike eigenvectors and eigenvalues, you only have a single basis. Here you have two. And notice the two bases satisfy eigenvalue problems, right? So here they are.
It be sigma squared.
That's true. Yeah, I think that's right. Yeah, sorry. Yep, thank you. Okay, so you have this, and notice then V are the eigenvectors A star A, U are the eigenvectors AA star. They share the same eigenvalues, and AA star and A star A are both Hermitian. So the formulation here is that these two matrices, they are Hermitian, which is exactly, in some sense, the easiest thing to compute eigenvalues for, right? Because there's all these really nice properties around these matrices. And so this allows us the ability to say, if I want to compute the SVD of any matrix A, which is not Hermitian, I go write these products which are Hermitian, which then, because of these properties, allow me to come back and give you U, V, sigma. Okay? So this is fantastic news for us, which allows us to do then, in fact, the way that this algorithm is going to work actually is due to a very famous algorithm from the 1960s. And by the way, Gene Golub at Stanford was the one who really pioneered these computational methods for the SVD. And this is a huge contribution to scientific research. This transformed computing to be able to actually go about and find algorithms that stably compute this for pretty large matrices. So I'm going to highlight this Golub-Kahan technology, if you were, as it will, from that time period. And of course, there's some things that are different now, but a lot of the same basic infrastructure from then carries over to now. And here's how this thing is going to work. You're going to start off with a matrix A. And what they did, instead of putting this in a form of, either upper triangular or Hessenberg, what they did is said, hey, let's actually go ahead and transform this to a bidiagonal form. So there's the main diagonal and an upper diagonal. Okay, so we're going to talk about how that method works just here in a moment, but that's going to be the goal. I'm going to take this matrix, put it into a bidiagonal form, and then the second step of this is take that bidiagonal form and iterate it to get a diagonal. So this is sort of the basic structure of computing the SVD of a matrix A, okay, is to start thinking about, well, those are basically computing eigenvalues and eigenvectors of these correlation matrices, A star A or AA star, okay? And we're going to do this through this kind of two-step process. Again, all these eigenvalue problems are two steps. Step one, do some kind of principled manipulations to reduce the matrix to a simpler form, then do iteration. And that's what you're getting here, okay? So we're going to do that same thing for the SVD. So let's talk about how to do this Golub-Kahan trick, or Golub-Kahan bidiagonalization. I want to focus on this step right here, from here to here, okay? And here's what's interesting. What I just showed you before, right, is this Schur decomposition where I use this matrix Q and Q star. The real advantage of the SVD is that, notice what I have. I have two bases to work with, two unitary operators, but U star is not equal to V star and so forth. In fact, I'm going to use two bases to perform this Golub-Kahan trick. That's the power of the SVD, is you can start already understanding that I'm going to work with two bases. And by using with two bases, what I'm going to be able to produce for you is this bidiagonalization, which is going to allow me then to finish this thing off with an iteration to the eigenvalues. So let's talk about how it works. So you're kind of getting the nuts and bolts of the SVD. In other words, the SVD itself is an eigenvalue solve. Okay, so a lot of decompositions end up being something like this. And the SVD has this eigenvalue structure underneath it. And so you're using eigenvalue solvers to get your singular values. You're using V's, which are left and right singular eigenvectors, if you want to think of them that way. So let's talk about how this works. I start off with a matrix A. Okay. Now what I want to do is I want to reduce this to a bidiagonal form. I want to get it to like a diagonal down the middle plus an upper diagonal. So here's what I'm going to do. I'm first going to multiply this by some matrix, a unitary matrix. I'm going to call this U1 star. And what I want U1 star to do is I want U1 star to zero everything out below the diagonal, the main diagonal I'm looking at. Okay? So far it looks like LU, or that in the Q's I did before when we were doing Schur decomposition, I zeroed everything out. I was trying to get for a tridiagonal form or a Hessenberg form. So I left this X, I left that not zero everything out here, but here it's bidiagonal. I want to zero everything out below the diagonal. So I find a U that does this. And again, we kind of know how to do this through looking back at our LU decomposition. Except for now, what I'd like to do is think about what can I do next to put this in upper triangular form, which is I want to multiply by another matrix. Let's call this V1. So I multiply this on the left, U1 star A. And then, and by the way, this doesn't have to be a square matrix anymore. Whereas what I just showed you before really, well, actually, when I showed you the decomposition with the Q's, that was sort of really assuming a square matrix. Now we're just, this can be tall, thin matrix, short, fat matrix. And so your left and right multiplies are different size matrices, right? U1 star multiplying on the left is different than V1 on the right, right? If I have an M by N, these are going to be different size matrices. One's going to be size M, one's going to be size N. What I want to do with V1 now, though, is I would like to clear, I want bidiagonal form. I want all these to be 0 in that first row now. So I'm going to work in row space, X, and make this all zeros, X. And now I want zeros all the way to N here. Something like this. So this is U1 star A V1. Is it starting to look familiar to you? Multiply on the left by one set of unitary transformations, on the right by another set. This is the heart of SBD. You can use two unitary transformations, one on each side, two coordinate systems to do this reduction. And you see I'm starting to do it. What I'm starting to do is remove elements down here, try to make this zeros down here, and then I'm using the V to remove things up here. Okay? Let's do it again. Now I take that and I multiply now by U2 star. So I have X zeros. Now I want X zeros. And here on the first row, I get this. So forth. That's U1 star. That's now U2 star, U1 star, A, V1. And now I multiply on the right, which now clears out all these zeros over here. So now I have X zeros. And then now I have 0, X zeros. And then these are all zeros here. These are all zeros here. Something like this. So I'm just going to progressively work my way down this thing. Clear out the next one, clear out that, clear this, clear this, clear this, clear this, all the way till I have, in fact, that bidiagonal form. Okay? Now, once you get this thing iterated all the way down to B, and B is a diagonal form, I'm just going to make comments here because two things. One, we're running out of time. Two, it's a whole nother set of lectures to explain the iteration on that bidiagonal form. And in fact, we're going to talk more about just iteration generally in the next few lectures. So I'm just going to leave it down the road for you to think about. This is the form I want it in. And then from there, I'm going to iterate to conclusion. From about the 1960s to about the 1990s, so about 30-year period, what you did here to take this B towards the eigenvalues is you used a QR decomposition to do this, or a QR algorithm, basically an iterative QR algorithm that allowed you to go from bidiagonal to diagonal. And once you had it in diagonal form, you had all the eigenvalues and eigenvectors. Okay? So that's a 30-year period where that was the dominant algorithm. In fact, the QR algorithm was famous partly because of the fact that once you did this Golub-Kahan decomposition, it allowed you to finish this thing off in an iterative way that was very fast to converge to eigenvalues. You remember the computers of the 1960s were exceptionally slow, right? We take it for granted that, any one of our iPhones or smartphones is probably would have been a supercomputer back in those days, right? And so computing they really needed fast algorithms. And so everything you could do to actually do a computation at any reasonable scale, this was one of the first algorithms that really could do these kind of things at scale, converge to eigenvalues, eigenvectors. And so this Golub-Kahan was really a famous algorithm in its time. But since about the 1990s, you trade out here QR iterations for what's called a divide and conquer. And the divide and conquer basically breaks up the space of the where eigenvalue ranges live, and you go look for eigenvalues in different areas of eigenvalue space. In other words, in the complex real versus imaginary lambda plane, you can go look for eigenvalues there in a prescribed and principled way. Very much like when we did the last lecture on when we combined the Rayleigh quotient with iterations. So the Rayleigh iterations at the end of that lecture, we always decided to move this thing around by mu to go look for eigenvalues in certain areas. You can do something like that with divide and conquer, but you can go look at lots of areas at once. You divide the region up of where eigenvalues can live, and you go find progressively each eigenvalue in each region. So that's the divide and conquer is kind of a state of the art today. So that's been actually now for 30 years. So if we look at the 60-year history, really, so we're in 2020 now, this is 1960. So we're got like the 60-year history, about the first half of that history, you get to here, then you do QR iterations, and since about 1990. By the way, 1990, that's like, that's when grunge was in full effect here in Seattle. So anybody in Seattle, we had, Pearl Jam, Alice in Chains, Soundgarden, Nirvana. They were all like hanging out in Seattle. I missed my time with them because I was just like studying all the time. I should have just been out being a rocker, big hair, black shirts. It'd been awesome, but whatever. I mean,
still got the black shirt.
I got the black shirt. Yeah, I do. They would have laughed at this blazer, I think. But there are worse things in life than being laughed at by Chris Cornell, maybe. So, okay, that's it. That's where I want to finish. And what we're going to go into is iterations next and talk about the power of iterative schemes to solving AX equal to B or eigenvalue problems, because that's a really important technique that's available for solving these linear algebra problems. And I'm going to go ahead and stop there, take questions.